So thanks everyone for joining, and especially thank you to James, who will hold this webinar today. James Custer is the team lead of the team developing the Cray performance tools. So he knows, I guess, everything about it. And we are really looking forward to learn from you and to learn from experience. So thanks a lot, James, for holding this webinar for us today.
Thank you. Yeah. I wouldn't go as far to say that I know everything about it. You know, we've developed this tool for, I think, almost 20 years now. So it's you know, we have a lot of history here, but yeah, we definitely keep everything up to date with the tool, and I'll show you all the features today. Let's see here. So what is Perftools? So Perftools provides an integrated infrastructure for the measurement, analysis, and visualization of your computation, communication, I/O, and memory utilization. So we provide the option of utilizing sampling, tracing, or a hybrid mode that we call trace enhanced sampling. So this is where you can have traced functions, but any functions that they call return a sample that's mapped back to that traced function. So there's definitely a lot of different ways that you can instrument your program to get good scalability. Language support, we support C, C++, Fortran, and coming up soon, which I'll talk about at the end for some of the things coming up on our roadmap, we'll have Python support as well. You can, so the programming models that we support are CUDA, HIP, MPI, OpenACC, OpenMP, OpenMP target offload, SHMEM, UPC. So we support all these different parallel programming models. We also have predefined trace groups. So these help enhance the readability in the reports by automatically categorizing certain metrics by these groups, and we'll see some examples of that later, such as with MPI. And we have I think about 30-ish different trace groups. So anything, we have third-party stuff along with system stuff. So you know, we trace BLAS, LAWPAC, FFTW, HDF5, and then you know, system stuff like standard IO, system calls, etc. So these are things that we can automatically trace for you, and you don't have to, you know, specify any extra options for those. You can instrument all user functions, or provide a list of specific functions that you want to trace, and you can enable or disable trace groups at will. We provide an API for fine-grained instrumentation that you can use to describe regions of code, or to enable or disable profiling of those regions of code. In addition, we provide GPU accelerator information, such as kernel execution time, data transfer sizes, the copy time between the host and the GPU. And this is all aggregated similar to our CPU code, where you can look at the profiles, callers, call trees, source and line information, etc. And with our GUI, you can utilize the timeline view to correlate the CPU and GPU activity. The most important part, well, there's two important things that we highlight with Perftools. One is the user experience, the usability aspect. It is extremely easy to use Perftools to get started with it. And you can dig down as far as you want into analyzing the performance with it. The second thing is that it's extremely highly scalable. So we've had customers that have profiled their applications with up to 256,000 ranks. And we have extremely low overhead. Even with analyzing, so with sampling, you can typically get less than 1% to 2% overhead. And even with a large scale GPU tests that we've done, we're still at that same level. Tracing incurs more overhead, but you can do hybrid stuff with it. So there's different methods that you can utilize to profile your application in a highly scalable way. So how do you get started? The most important page that we have would be our intro Perftools man page. So all you have to do, you log onto your system and the Perftools base module is loaded, and you just type in man intro Perftools. Secondly, there's a user guide. It's a bit hard to find, so I'll pull that up right now. So if you go to support.hpe.com, and if you were to type performance tools, you will see the first one that pops up is an older version. So you have to be a little bit careful here. What I would actually recommend is, so you could either sort by time, which then you'd have to scroll a bunch, or I could provide you with the exact document number. So if you search by this S-8014, you'll see that there's the document here, HP Performance Analysis Tools User Guide 2205 is our latest release. So I recommend that you search by this document ID, sort by time, and you'll get our latest document. I know that that's a little bit of a hard thing to go through. I will mention that we're actively working on updating this for a better user experience. So this is something that we're working with our transition to HPE and how to best provide our documentation. So this will bring up a PDF for you that has the user guide. So this goes through the different overview of what the tools are, sort of examples of how to get started with Perftools, Perftools Lite, Pat Build, etc. And it walks you through how to use the GUI and reveal. So my talk today will be somewhat similar to the user guide, but I'll be giving you a lot more hints on how you can actually best utilize it.
May I just make one remark here?
Sure.
For everybody who is now testing this on Ookami, getting the man page, you first have to load the CPE module, so the Cray program environment, and then the Perftools dash base module, and then you can do all of that too.
Yep. So yeah, and also on the system that I'm on, yeah, if you do a module list, you'll see here that I have the Perftools dash base module loaded. And then we have what we call an interactive help tool called Pat Help. So this is basically a Perl script, and we utilize this to put some documentation in for certain things that would basically blow up the man pages to a humongous size. So you'll see here that if you execute Pat Help, and it's a Perl script that has tons of stuff, so it might take a couple seconds to launch there. And then basically you have a new entry portion here, and you have topics which you can jump into. So, if you're interested in certain things like Pat Build or the API, there's also some frequently asked questions in here. So you can just type in what you want to go to. So if I go to the FAQ, and you can just basically keep going, diving deep into the topics that you're interested in, and you navigate by the shortcuts here. So if you want to go up a level, you just use the caret. Quit. And I'll show you an example of using that in a little bit. So So how do you actually use Perftools? So make sure that you have, first that you have Perftools base module loaded. Then there's a few different what we call experiment modules. So if you do a module avail Perftools, you can see that here's our experiments. So there's Perftools, Perftools Lite, Perftools Lite Events, Perftools Lite GPU, HBM, Lite Loops, and Preload. The way that you can get information on these, so if you were to read the intro Perftools man page, you'll see that, so it gives you an overview of the different types of things that we have. And then in here, it gives you a list of other man pages that we have. So one of those is the Perftools Lite man page. So if you do a man intro, man Perftools Lite, you can see a description of each of these. So what I'll walk you through today is, what should you start out with? What you should start out with is the Perftools Lite module. So as I said before, there's multiple different methods that we can instrument the application. So we can either do sampling or tracing. Those are the two main methods, or the hybrid mode. So Perftools Lite will give you the sampling method. Perftools Lite Events will give you the tracing method. So if you want to utilize the sampling, Perftools Lite, you load the Perftools Lite module, and then you simply compile and link your application as normal, and then just execute your application. So what you'll get out of this, so the reason why this works, and there's a little catch that you have to ensure with your build process to make it work. So as long as your application build system is using the lowercase cc, uppercase cc, or the FTN compiler functions, those are our wrappers, then this will all work seamlessly. So if you're not utilizing those wrappers, you have to do a little bit of extra work. And I'll talk about that in a little bit. But as long as you use those wrappers, everything behind the scenes gets automatically instrumented for you. So when we load that Perftools Lite module, we have things in that module that set some environment variables, and then those wrappers read those environment variables and say, hey, I know that we want to instrument with Perftools, and during your compilation, we automatically inject some compiler options. And at the linking stage, we have our own link wrapper that links in some of our Perftools libraries. And so what you'll end up with after you build your application, you'll end up with two executables. One is your original executable name, and that original executable name is now your Perftools instrumented binary. And then the second executable will be your basically the original executable name plus orig, short for the original executable. So you'll still have the original that you can run without having Perftools do any instrumentation. And so at the end of the execution of your application, you'll automatically get a report that pops up, and that'll be the pat report of your application. So let me jump into an example here. So I have a few different experiments that I've ran. So I've ran this with a program called Sweep 3D. And the first one we're going to look at is the light mode. So what this has is, so we built the application with Perftools Lite module loaded, and the report that we get out would be this report here. So at the beginning of your application, you'll always see this line. So this line also comes up in the report. So this line, as soon as you execute your application, you'll see this Cray pat line, and that'll indicate to you that your program is properly executed for using Perftools. And then at the start of the report, we also have this line, and then we have a summary of the system. So we have the number of PEs that you used, or the MPI ranks. So in this case, it's 100. And it gives you how many PEs were used for each node. In this case, 20 per node. Number of threads per PE. And this is if you're utilizing OpenMP or something. The number of cores per socket on the system, the system name, and the nominal CPU speeds on there, with the exact CPUs that were used on that system. And additionally, the amount and speed of the RAM that's on the system. So then you jump in, you get various tables. So each of these tables could differ depending on the type of experiment that you're doing. So we simply enumerate the tables here, but typically you'll see the name of the table is correlated to an actual file that I'll show you in a little bit. So this table 1, we have a description here that says, this table shows functions that have significant exclusive sample hits averaged across ranks. And it tells you that you can also view some more information if you execute a command. So like I said, with Perftools Lite, you'll automatically get this report at the end of your application. So you don't actually have to run any commands to see this report initially. But if you want to do any follow-up analysis, you'll utilize the pat report command on your experiment directory that gets generated. So for this one, we have significant exclusive sample hits averaged across the ranks. And so for this application, everything is presented in this hierarchical table. And so as you look at this table, you'll see these the things on the left indicates the levels of the hierarchy. So this indicates the top level, and then this indicates the second level. And so everything, as you go up the hierarchy, everything gets aggregated up. Okay, so additionally, you'll see these portions here, which separates the different groups. So you can see that this is actually at the top level. So we have the total is separated into user, MPI, and etc. So these are essentially the different, what I call the trace groups before. So this would indicate the MPI trace group, and all this other stuff is just etc. stuff. And then user code is anything that, so the way that we define user code is when you build your application, we actually look at the source files or everything that's been compiled through your build system, and anything that is owned by a user is considered the user code. Anything that's in sort of like a system directory, we consider that the non-user code. So if you do have a sort of a third-party library that you're using that's compiled within your directory that's owned by you, that will still show up as, that'll show up as user code. Whereas if it's in something like user include, if it's in there, that'll show up as non-user code. So just some hints there. And the other thing to mention here, so you'll see that we have samples, so not time because this is sampling. And then there's this imbalance. So since we're aggregating across the ranks, we can measure this notion of imbalance to say, this imbalance 20% means that this number here, this sample here, is the average across all the ranks, but this is sort of the deviation from that average that other ranks experienced. And you can see the exact definition by putting this verbose mode on this table file. So let me show you that real quick. So if I wanted to say, okay, what are the exact definitions of everything within this table? We can run this command. So notice here that I have this directory, and there's the way that we named it here was this .expdir. So we know that that's our experiment directory. So if I do pat report -v -o samp profile and give it this experiment directory. Let me clear my screen real quick. Now, notice that the entire report, sort of the footer and the header also came up. So when you're looking at individual tables, such as this, there's an additional option that you can put in there to sort of get rid of that clutter. And I want to show you that because it's pretty useful to only focus on what you're interested in. So that's a -s content equals tables. Sorry, I can't see my screen. So now we've gotten rid of that header and footer. And so we're only showing the table with the table header. So this is the part that we saw before, was just this short version of the header. And now we see all this extra information. Now, what I want to make clear here is that the information that's provided in detail here is not fixed information. So this explanation is actually dynamically generated based off of what the actual table is showing, right? So this information will be different depending on which table that you're looking at, and it'll exactly correspond to what columns are available. And I'll show you in a little bit that you can define your own tables, your own custom tables, and this detailed information will dynamically adapt to your custom table without you having to do any extra work. So what this portion here tells you is the options that were used to generate this table, and then any options for related tables, right? So this is the sampling profile table, and it's telling you, hey, some other tables that you might be interested in that are similar to this table would be like samp profile plus source. And that'll give you the source lines for any of these samples that were hit. And it gives you the definitions of each of the things under here. So since we're aggregating by group, function, and PE, so we're aggregating, so group would be this user, and then it's looking at the functions, and it's aggregating by PE, but it's hiding the PEs. So if you were to show the PEs, what you would end up with is you would still have this line that's aggregated, but underneath each of the functions, you can see the exact timings for every single PE that you want. And it tells you that the function value for SAMP is the average of all the PE values. And notice here that, so this is an important thing that comes up with for new users is they'll say, hey, I don't see functions that I actually have defined in my program. What's going on with that? Well, by default, we only show lines with a sample percent that's greater than 0.95. So basically, you can think of that as, we only show stuff with samples that are 1% or greater, or 0.95% to be exact. Then it gives you the definition of the imbalance. So the imbalance percentages are relative to the PEs. If you look at the man page gives you the exact formula that's used. Okay, so I've talked a little bit about the different the tables that exist in these, and I keep talking about these -O files. So each of the tables that are presented each of these tables that are presented in the report, like I said, are defined in these -O files. So how do I know, how can I see what those definitions are? Or we actually have a bunch of other tables that are available that are not included in the default report. Okay, so how you can get access to those is if you do a pat report -O, and then you use the help option following that -O option. So if you do that, that'll give you a list of every single possible table that we have predefined. Okay, and so here we know that first table was this SAMP profile table, because that's what it told us in the help. So if you want to see the definition of that file, you can say pat report -big O SAMP profile, and then add the help option to the end of that. And adding the help option to the end of that gives you the exact definition of that table. So if you look at the pat report man page, the pat report man page describes exactly what all of these options mean. So you can think of it as the -B options are the things that you're aggregating by. So here, we were doing group, function, PE, and thread. And then the -D options are the columns of your table. So you can see here it's that we're doing samples, but there's a min sample percent that we use internally. So we define that internally to be that 0.95. And then samples not as a percent. So this is sample percent at that min SA percent. And then the samples, imbalance sample percent. Then this other stuff just tells you, can define certain things that modify the table. So this tells you what the ID of the table is, tells you the purpose. And this is the part where we said, okay, we can hide those PEs and hide the threads, show all the functions. And then this is actually where those related tables come in, because these are our predefined ones, right? So suppose that we wanted to show all of those PEs. Well, first of all, you would go through and you would look at the predefined tables to see if you already have one. In this case, we don't have one that automatically will show you all the PEs. But what you can do is you can say, okay, I want to edit this table. Well, you could just run the same command that you did with the help option. And then I'll call this SAMP profile PE. And I'll just output that to a file, and I can edit it. And if I go down to PE, I can change that to show. And then now, if I want to show this single table, and if I want to ignore the header and footer, I can say -S content equals tables to get rid of that header and footer, -big O, and then I'm specifying a file here. So if you if you don't specify this relative path or the full path, it goes and it looks for these predefined tables. So I want to put a // here that's in my current directory. And then I need my experiment directory. So typically what you might want to do is if you're doing a lot of these manipulating of the pat reports, you can also simply just go into the directory. And just notice here that I just wanted to point out that there's multiple directories in here that contain the original XF files and the AP2 files. So once you've generated a report, at first you'll get these AP2 files, and that makes looking at these reports a lot quicker. But anyway, so if we run this command, and instead of supplying the name of that directory, we can just put the current directory, which is just the dot. That makes things quicker. Oops, except my big O file is now in the directory above me. So now we have all the P's, and like I said, we have 200 of them. So this might get a little unwieldy. So here is our profile by function, and then we have the sweep function, and then you can view the exact timings. Note that there's no imbalance information here because this is at the individual PE level, so there's nothing to aggregate for the imbalance. So you can see the exact timings here. So that was just a quick way to show you how to customize a table. Let me go back now and show you sort of what else do we provide by default. So I'll do my pat report dot, and so pat report with no options just gives you the default report. So here's table 1 that we just looked over. Table 2, so this is all the default reports. So this is what you see at first glance. So what we put into the default report are things that we think a user will find useful to identify the most common bottlenecks, right? And so the usefulness of being able to edit the tables, to dig in deeper is useful if you don't see a real obvious bottleneck at first, or you've identified a bottleneck and you want to dig deeper into it. Okay, so the second table, we provide the max and min function times. So this gives you, so whereas the imbalance gives you sort of that idea of how imbalanced things are as over an aggregate, the max and min will show you what that actual range is between the max and the min. And then in between some of the tables, so specifically with the default report, after the first 2 tables, we generate a set of observations. So you won't see observations for every single report, but basically when we detect certain things about your application and they've exceeded some threshold, we will generate these observations. So one of them, especially when you're working with MPI applications, is that we automatically look for grid type communications, and we look at the actual communication for point-to-point stuff and say, okay, is there actually a different order that we could make those ranks to speed up that communication pattern? Okay, so in this case, we've identified, so there were 20 PEs per node, if you remember. So, and you can see here that it detects a grid. So it shows that there's a point-to-point grid of 5 by 20, and that 44% of the total execution time was spent in MPI. And you can actually see that from the first table, if we scroll back up. So the number of samples, correlating to the amount of time spent in the application, we can see that it spent 44% of time in MPI here. And so it's saying, okay, I'm gonna attempt to use some different rank orderings in an attempt to speed up your application. So we suggest different kinds of rank orders. So we do SMP, fold, or round robin, and then we do a custom graph-based optimization ordering. And what this will show you is an estimate. So an estimate as to how much on-node bytes per PE that you would have for if you were to use these rank reorders. Okay, and so based on this, if you utilize the custom rank reordering, you would get the most on-node bytes per PE. And so what happens here is once we've detected this and we've done this reordering, you'll get a file that's generated in your experiment directory that contains this mpitch rank order .grid. And then when you execute your application again, you can utilize that rank reordering to send that to your workload manager, and it'll execute with that different rank reorder, and you should see a speed up of your application automatically without even modifying your code. You'll see here we have some other observations. So we also have a metric-based rank order. So we use some default metrics here to also suggest a different rank ordering. And you'll notice here that so this one is based off of MPI, point-to-point communication. But a metric-based rank reordering can be used to say, okay, if you have an imbalance based off of a certain metric, is there some other ordering that we could use to speed that up? So where that might be useful is if you're accidentally, if you're on a multi socket system and you're accidentally accessing memory from farther away than you should be, and you can reorder your ranks that way. Let's see here. Another important one here would be stall cycles. So when we analyze the stall cycles of your application, and our default threshold is 40%. So this is an indication that you should look at any issues that are causing memory bandwidth saturation, and to see if you could possibly speed that up. So to analyze this stuff, you'll have to dig into the CPU hardware counters to look into this. We also look at memory latency. So this observation says that the relatively low memory bandwidth utilization but significant rate of stalls suggests that your performance is limited by memory latency. So it suggests that you could use prefetching in your loops in functions high in the profile by modifying compiler generated prefetches or inserting directives into the source code. So here it says in loops in functions high in the profile. So if you scroll up here, well, our largest profile is this sweep function, right? So this particular benchmark, there's a lot that goes on within this sweep function, and there's a large number of loops. How do you actually identify those loops? I'll talk about that in 1 minute after I finish talking about the rest of the report here. Sensitivity to vectorization. So here we analyze the vectorization, and for this it says the program did not appear to be limited by low vectorization. So there's nothing really to do there. the next table, we show a profile by the group, function, and line. So this is a way for you to say, okay, well, I'm looking at my application, and within this function, I can see line by line where the samples hit. Okay, so so this allows you to map it back to the source code. And we also provide the file that was used at the upper level. And then finally, we show the hardware performance counter data. So by default, when you're doing this light experiment, so we're doing sampling and hardware performance counter instrumentation. So you'll be able to see all these default metrics that we use for the hardware counters. So we'll see cycles, retired instructions, stalls, the CPU clock, any boost that occurs. And then we have what we call these derived metrics. So these all caps ones are typically, CPU counters that are just the native CPU counters. And then stuff that's not capitalized and sort of like this are derived counters. So here we measure stall cycles, resource stall cycles per cycles, floating point packed instructions as a proportion of all the instructions of the application. So that's really low. Any memory traffic, what's local versus remote memory traffic. So here, we want the local memory traffic to be super high and the remote to be super low, so that we utilize the NUMA architecture properly, and retired instructions per clock and things like that. So since we've since we've collected these hardware counters, this is where we get the information to generate those observations that we saw above. So if just a note there that if you later do a custom, if you don't use the light mode and you do a custom experiment of your own, you might not see some of those observations based off of the hardware counters that you're collecting. Next, we do file IO. So you can see the input and output statistics for this. So you can see, how many ranks we're writing or reading to the files, what their rates are, the number of bytes per call, etc. So, this will let you see, how much time that you're spending in IO, and is there a way for you to sort of coalesce that reading or writing to speed things up? What might be your IO bottlenecks. We also provide some luster information, and we also provide power usage. So at the node level, for the duration of your application, we tell you how much energy was being used for each of those nodes. And then finally, we have memory related information. So you can see the high watermark for each of the NUMA nodes and the memory bandwidth per NUMA node. And the last thing that shows up in the report is just your wall clock time, along with the high watermark per PE. So, so this here, this is when you see the brackets MMM, this is giving you the mean, median, and mode of your application. So that's why there's 3 things that show up here. So if your overall process time is way off, you might want to check that. And then finally, in the footer, we give explanations as to how things are defined for all the tables in general, and then for certain things like sampling interval. So when we do our sampling, you can modify your sampling interval to be whatever you want. And here we show which one was used. Additionally, we show, how was this program actually instrumented? So when you're using the light mode, here, this is something that you don't see at all, because we did this automatically for you when you built your application. But you can utilize this and customize it however you want. It gives you some environment information for your program. So if you want to collect things, about your exit status and see, which of the PEs have a different exit status, that's presented here, or the different page sizes, huge page size, which programming environment you were using. So this information is typically useful if you're doing multiple different experiments and you're comparing. So say you're comparing different compilers or something, you can make sure that when you go back and look at the reports, things make sense to yourself. And it will show you environment variables, etc. Last thing, the thing that would be most important here for you to look at the bottom is when you're collecting the hardware performance counters, we give you the definitions of those counters and what was used as the derived counters. So that's why you see things here where you see a counter, colon, another counter, colon, another counter. So those came from our derived metrics that you saw up above. Okay, so I promised to show you about the loops, right? So if we have, up here in the first table, we had sweep, but we don't know which of those loops might be taking up the most time, right? And down below we had the source information, so we had hits in the line numbers, but we would have to manually go and see, okay, which loop does this line number correspond to, etc. But we actually have an experiment for loop information. So if you do man Perftools light, you can see that we have Perftools light loops. Okay, so this will give you loop estimates. Normally, this is also used for reveal. So reveal is our parallel programming porting tool. So you can use this loop information to convert your loops to OpenMP regions to help speed up your code. I won't be talking about reveal today because that's a much bigger topic that we could spend a couple hours on, but I wanted to give you an introduction to this loop experiment. So with Perftools light loops, how do you use that? Well, with all the light stuff, you use it just like you did Perftools light. So you load the Perftools light loops module, compile your code, and execute it. That's it, right? And so we can move up. Let's see here, go up a directory. I already have this stuff all prepared. So I'll go into the experiment directory for the light loops. So I'm not going to go ahead and run the pat report command. I'm just going to look at the report that I've generated. So what does this give you? So the light loops gives you similar tables to what you saw with the Perftools light module. So if you don't want to reread these, you can just scroll down more. So down here, so table 3 is the most important table for this experiment if you've already looked at the Perftools light table. So here, what it shows you is the nested view of loops that have significant inclusive time that's averaged across the ranks. And so any function calls in these loops, etc., are not included. So this is just showing you the inclusive time for all of these loops. Okay, so you can see here that we have this inner loop and sweep is called by this inner loop. And we have each of these loops, and it shows you the exact line numbers, right? So, and then the inclusive time here, right? So, so you can utilize this to help identify which are your hottest loops. And you can go and say, okay, well, I know these are my hottest loops. How can I, can I vectorize these loops? Can I convert them to OpenMP regions? Can I, do prefetching for these loops, etc. So this is the information that you can use to help drive those decisions, right? And so you can see here, it gives you the number of times that the entire loop was executed, and then the trip average. So how many iterations per execution of the loop was performed. Okay. So that's the main useful table here. If you scroll down, there's just the additional stuff that we saw before. Okay. So that covers Perftools Lite and all the tables in that default report, along with how to get information about your loops. And so that was with sampling. So how do we do tracing? So with tracing, that's what we call the light. Man. Perftools Lite. Okay, so that's what we call the Perftools Lite events experiment. So Perftools Lite sampling, Perftools Lite events tracing. So if we look at the events, clear my screen. So what's different here? Okay, so the main difference that you'll see here is that instead of samples here, we have time. So what happens here is that when you do tracing, we actually instrument these functions themselves, and so at the so we essentially wrap these real functions, right? So this driver underscore here, there will be a wrapper around that function, and then at the beginning of that wrapper, we can start a timer. And at the end of that wrapper, after the function has returned, we can end the timer and we can measure the exact time spent in that function, rather than relying on samples. But as you can imagine, if your application is humongous and you're calling, billions of functions or something, tracing can incur high overhead, especially for very small-lived functions. So if you have, functions that are, executing, very quickly for many times, the overhead is much greater compared to if you have, a function that's executing over a long time. The overhead of tracing is much less pronounced. Okay. Oops. Sorry. So the difference between, so that's the main difference. The other difference that you'll get is the actual number of calls for the function. So when you're utilizing sampling, you don't know how many times those functions were called. You just knew how many samples were hit within that region, right? So so you get exact function call counts with these. So the other thing that I mentioned was, users at first might be confused as to why they don't see all their functions showing up. And I told you about the thresholding, right? So, so one option that you can give to Pat report is to disable that thresholding. So if I do pat report dash big T, my current directory, we've now disabled thresholding, and we see every single function that was called within the program. So what else do you get out of tracing? Well, you can get more MPI information. Okay, so you'll see here that, well, let me turn off the thresholding. So we have our observations still. Notice that we don't have any of the vectorization stuff, because with the tracing with this experiment, we didn't have hardware performance counters enabled. But with tracing, we can get more MPI information. So since we're performing the tracing, we've wrapped these functions and we have these predetermined trace groups. We have the API information from MPI. So we know what information was provided to those MPI routines, and we can grab things like the amount of data that was sent or received, or how many exact messages were sent or received. And so what you can do is you can look at, now you'll have a table where you have a load balance for MPI. And so for here, we'll say, over with this MMM, we'll see the mean, median, and mode for these. So if you're seeing a huge difference here, you know that your MPI could be imbalanced. Additionally, you can see which MPI library functions were used to send a significant number of bytes. And so we can get basically histograms of these different MPI routines, right? So here's a total. So you can say, okay, for all of the MPI stuff, here's a histogram of the number of the count of the messages, and then the distribution of the sizes of those messages. So you can see here that most of these messages, lie between 64 kilobytes and a meg. And you can utilize this information to make sure, that you're not sending a billion very low message counts or something that, if you're latency bound. And then within this, you can see there's a hierarchy here, right? So as you dig deeper, you're digging deeper into the tree here, and then we can separate it out by the different PEs for that mean, median, and mode as well. And for this information, for this table, you can theoretically edit the table and show every single PE if you wanted to. But I'll show you a better way to look at that with the GUI in a little bit. Okay, and so the rest of this information overlaps with what we already saw with the sampling report. Okay. What else is there? So suppose that you have an extremely large application. Your first go around for analyzing that application is going to be the sampling method, right? And then, but if your application is so large that you're concerned that if you want to dig deeper, that tracing might be incur too much overhead, we have another method to instrument your application to help guide you as to what should you trace. Okay, and so this is called our automatic profile analysis method. So the way to use this, and I'll tell you how to get access to this information. So if you do a man pat build, first let me explain why I'm looking up pat build. So if we go back to our slides here, a more complicated example for not using light mode So if you want to, dig deeper into your application, you have to go beyond the light modes. And so, how do you do things then? Well, rather than using one of the light mode modules, you'll do a module load Perftools, compile your application normally. And now here's where you have to be aware of the differences in your binaries between the light modes and the Perftools module method. Okay, so in the light mode, I said the binary that you get out is your instrumented binary. And then you have a plus a ridge version of your binary that is your uninstrumented version. Things reverse when you use the Perftools module. So the Perftools module, you compile as normal, and then the binary that you get out is your uninstrumented version of the binary. And the reason why we spit that version out first is because we set up some initial information that we need for your binary. So we've instrumented it with some stuff that doesn't actually affect the execution of your application. But then once you utilize the pat build command, that's when we decide, are we going to which functions are we going to trace? Which trace groups are we going to include? Or if you're doing sampling, et cetera. So from here, you take that binary that gets spit out, and then you perform pat build with some various options that you want, and apply that to the binary. Then the binary that will get spit out for that by default is the original binary name plus pat. So there's multiple different options that you can provide to pat build, right? So you can say -u will trace all user functions, and then the -g option, you can specify trace groups. Okay, so in this instance, I've said, let's do a -g MPI. So that'll trace all user functions and MPI routines. Or, as I said, you can utilize the automatic profiling analysis mode. And what this does is essentially you'll do a sampling experiment first, and as part of that experiment, it'll spit out a file, and that file will tell you, hey, based off of my analysis of your application, I suggest that you trace these certain functions because these are hot functions, right? Or it looks at the different types of routines in there, and it'll detect. So if it detects like MPI was used, then it'll say, I'll suggest that you trace MPI as well, and things like that. So man pat report will give you information on all the options that you can use for that. So like I said, there's -g for the trace groups. Another helpful option for that is the -f. So if you're doing multiple different options for pat build, if you're performing pat build over and over again, then the -f option is useful because by default we don't overwrite the plus pat version of your binary. So -f will just force that to overwrite it. And as you can see here, these are all the lists of predefined trace groups that we provide. So like I said, BLAS, CUDA, FFTW, HDF5, HIP, LawPack, Luster, MPI, OpenMP, etc. So many different things. You can look through this list. And then -O will be useful when I talk about the APA stuff. And then I just wanted to point out a couple more things here. So you'll have the this dash T, dash big T. So dash big T, you can specify the exact function that you want to trace. Now, you have to be a little bit careful here. So for Fortran 90 and C++ programs, you have to use the mangled form of the name. Okay, so you can't specify, like a namespace ::, or something. You have to specify the fully mangled name. So if you use NM on your original binary, you can get the mangled form of the name for the functions that you're interested in. And then, like I said, -u, this will create trace intercept routines for functions that are defined in the source files owned by the user. Okay. And then -w basically says, I want to do tracing, but just use the default stuff that Cray uses. Okay, so where do I get information on APA? So if you scroll down, I just search for APA. There's a procedure here. So we say there's a section here on using automatic profiling analysis. So it tells you, okay, do your pat build and use -big O APA and your program name. Then execute your program as normal, and then you can look at the pat report. So what this spits out is, like I said, it utilizes sampling, and then within that directory, you'll have an APA file. So I think by default it's called build-options.apa. And I'm going to show you an example here in a second. And then once you have that, and you can edit that file as well to add stuff that we didn't detect or stuff that you just know that you want to include. Then you do your pat build again, this time providing that APA file. And what the APA file is basically is just a list of options that you provide to pat build. It's just we've generated those options for you. Okay, and then once you run your program again, you can do the pat report on that new experiment directory and get your results. So here I'll go to the job that I utilize this for, and so inside the experiment directory, you can see that it generated the build-options.apa file. So this is exactly what it generated, right? And inside there, it has comments that explains why it included things, and like why it suggested it. So, for this, it says, we want the default performance counter group, right? So what this is saying, set this environment variable to default. And I'll explain the performance counters, how to actually activate those in a little bit. And then libraries to trace. So it did not, this is saying disable the energy counters. And then it detected MPI, so it's going to say use the MPI trace group. And then user-defined functions to trace. And this is sorted by the percentage of samples. Okay, so and it tells you how it actually filtered out these functions, and you can go back and you can do your -big O APA, and you can adjust these thresholds if you want. Okay, and it's saying, okay, I want to do a tracing run with -w. And note that there's no -u here. So it says, note -u should not be specified as an additional option, because if you do -u, it'll trace all user functions. And, if you're doing this, you're concerned about overhead. So you don't want all of them. You just want to enable tracing only for a specific set of functions. Okay, so this is saying, hey, I detected, 43% of my samples, were within this sweep function. So let's trace sweep. And then for pat build, what it's saying is, here's my new instrumented binary. And by default, when you generate this APA, instead of a plus pat, it generates your original binary name plus APA. And then the location to your original program. Okay, so then if we generate the pat report here, so what this is saying is, okay, so now I've traced, oh, sorry. Oh, I didn't, oh, I apologize. I didn't include the other experiment directory. Okay, but what you would see, so this experiment directory is the original one that I performed with the -O APA, and that was the sampling experiment that spit out that APA file, and then you have to rerun your application with that new binary. And then what you would get out would be similar to that other tracing experiment that we saw, where we would see sweep now was traced. You wouldn't see any other trace functions except for MPI. Okay, so if we go back and compare it to the events, yeah, it'd be helpful if I pull this up to show you. So you would not see driver. You wouldn't see driver here. You would only see sweep. And if I turned off thresholding here, you can see all user functions. For some reason, sweep's not showing up here. I think I did something different. But anyways, you wouldn't see any of these extra functions. You would only see sweep and MPI because that's all that we specified for tracing. Okay. All right. And then with pat build, like I said, you can also specify, -U, -G, MPI. I'm going to skip over looking at that since I want to leave some time for questions. So I'm sorry, I forgot one thing. Okay, so if you want to specify your own hardware performance counters, how do you do that? Okay, so if you look at, I think, intro Perftools, there's an environment variable called pat RT perf counter. So what this says is you want to specify the performance counter events that you want to be collected. So if this is unset, then you are not going to collect any hardware counters at all. And to set it, you want to specify all of those events. Okay, so how do you know which events to set? So if you scroll down even further or just search for this, you'll see that so they're specified in a comma separated list. And then how do you actually know what the counters are named? Okay, so there's two ways of doing this. One, you can use PAPI avail or PAPI native avail, and you have to be careful here because if your login node CPUs are different than your CPUs or GPUs for that matter, different than the ones on your compute nodes, you have to run this on your targeted system, right? So if you want to look up the hardware counters for those specific CPUs or GPUs, you should log into the compute nodes first, okay? Or there's another way. The other way would be to look at pat help. The other thing as well is that PAPI native avail won't show you any of our derived counters, I believe. So you want to look at the pat help here. So we go into pat help and we just say counters. And then we have a list here of, so it tells you, if, the PAPI module is loaded, you can use PAPI native avail. Make sure that you're on the compute node, and it tells you that the runtime environment variable can't set the name of a derived metric. So that you have to look at the derived metric and you set the required counters to be collected for that derived metric, and then that derived metric will automatically show up in your report. Okay, so that's an important piece of information. So then it goes through and it says, okay, here's all the general list of hardware counter categories for different CPUs and GPUs. And then we have additional topics, which are basically just an expanded list. So short names for different GPUs and classes of those. So for instance, if you're interested in Thunder X2, you just type Thunder X2, and we have derived counters, groups of counters, native, and PAPI. So if I just type native, this gives me a list of all the native counters. And if I type derive, it gives me, these are the same, but I think it's under groups. Okay, I need to check why it's doing that. But anyways, so you can take these counters, and then you set that environment variable to a comma separated list of all these counters. Okay. Let me go through. So that's how you would set a custom list of your counters. All right. So this is just something that we've already seen. So I just wanted to point out, make sure that you look for these observations within your application, because if you see that the thresholds have been exceeded, those are likely hotspots that you should investigate. So for the GUI, there's different things that we can see with the GUI that might be better seen in a graphical representation rather than a text-based representation. Okay, so here with when we show the imbalance within a report, you might better visualize what that imbalance is within our GUI. Okay, so let me jump in and say, okay, how do you get the GUI first of all, and then how can you use it? Okay, so with how do you get it? So with the Perftools base module loaded, you have an environment variable that is defined called craypat_root. Okay, so this environment variable points to the base location of the version of Perftools that you have loaded. And then if you look in this, excuse me, there's a share directory, and inside that shared directory is a list of desktop installers. Okay, so we provide installers for Mac, which is the .dmg, or Windows, which is .exe. Currently, we do not have a general installer for Linux. So if you want to use the Linux client as opposed to the Mac or Windows, basically you would have to just do X11 forwarding from the login node. And you could use the Apprentice 2 on the login node system. But that is on our plan to try to provide a general Linux installer. Okay, so I've copied over the Apprentice 2 over to my Mac and I've installed it. How do I actually get information for that? So let me close this out. So you can either copy over your experiment directory to your laptop, or alternatively, which is what I almost 100% use, is our remote functionality. So Apprentice 2 will just act as a client and your data can still live on the server. And here I'm going to log into the server that I'm SSH'd into. Okay, and by default, it'll spit you into your home directory, right? So I'll go to my Sweep 3D directory. And now for this one, I'm going to load this full directory. Okay, so you can see it's really fast, right? So it loads up immediately, gives you a little bit of an overview of your application, how much compute versus programming model, the top functions, any load imbalance, the energy usage, data movement, and high memory. So for this example that I was showing, this is a different application here. But what we showed was the imbalance time, and we can actually just view the activity over all of the PEs, right? So for this one, I can click on the activity tab and we can see that it's generally well balanced, right? And so we can also, for a particular PE, you can hover over it and see the exact percentages there. You can also increase the font size a little bit here. Okay. Okay. So next, you can get point-to-point information. So remember when I said we were looking at the MPI table, and I said theoretically you could expand that list and show every single PE. However, with a GUI, this is much better visualized within a GUI. So you can come over here and you can click the mosaic, and this will show you the average point-to-point send and receive times. Okay, so and you can also do grid averaging. So you can say, one by one, or do some averaging for 2 by 2, etc. So, and then for each of these, so this is basically a heat map. So red would be larger average send times, and the greens would be lower. And if you hover over each of them, you can say, okay, this one's going from PE 9 to 10. There were 480 total calls, 73 million bytes. The total time spent for PE 9 to PE 10 sending information was 1.17 seconds, and the average time was 0.002 seconds. Okay, so for the send time, and then it also includes the receive time, so 8.9 seconds total time receive. So you can utilize this to see where do you have any bottlenecks with your point-to-point communication. Okay. Additionally, if you can also generate traffic timeline. which I don't have here because I didn't provide the correct options. But if you look in the man pages, you can see the correct options to generate this timeline. So with the traffic timeline, you can view for every single PE over the lifetime of the application, right? So this is a timeline view. So you can see how much time is being spent, doing a receive operation. So, all these blue things indicate a receive operation. And then the greens would be a send. And there's the red would be synchronization time. And then you also have all-to-all and broadcast. So using this, you can see where there are certain imbalances in your communication, and you could utilize that to help improve the overlaps of your computation and communication patterns. This was the table that we've already seen. So this would show you the different functions with their mean, median, mode, and distribution of the MPI calls. If you're doing GPU work, we also can generate a timeline for the correlation of the host call stack versus what's executing on the GPU itself, right? So here would be your host view, your host call stack, and in the middle is your GPU timeline. And you can correlate, how many streams are running, and when, what's occurring on the CPU during those, so that you can help overlap your offloaded GPU stuff and make sure that you're executing enough stuff on the CPU as well. Okay, and then the last thing here would be if you're only interested in certain regions of your application and you really want to limit the overhead, I've already talked about a couple techniques for that, but this is your big hammer. Okay, so here you actually edit your source code and you can insert what we call pat regions, so for this, what I highly recommend is you utilize this variable that is defined when you're instrumenting with CrayPat. So when you're instrumenting with CrayPat, we automatically insert a compiler option that says dash big D CrayPat. And so if you utilize these if-def wrappers around any of your region-specific code, then you won't have compiler failures when you're not using Perftools. And then when you do instrument with Perftools, these regions will automatically be enabled. So with this, what you'll end up looking at in your report is you'll see these region names. So for this one, the region is called just loop, and you'll see that region show up, and you'll get all the normal things that you have seen in the report so far. So if you're doing, if you're doing sampling, you'll see samples within that region, or if you're doing tracing, you'll see function calls within that region. Okay. One other important thing to note here is that you provide this with an identifier that has to be unique. But we recently have updated our API so that there's an alternative API that you can use where you do not have to specify an identifier, and nesting also works with that. But there's some limitations there, so you'll have to look at the documentation to make sure that it can still be useful for you. Okay, so the last couple of things that I wanted to talk about was our roadmap. So I've already indicated a couple improvements. So we're adding Python profiling, and we have some other various improvements that I mentioned. And then the last one that I wanted to mention was the apprentice to UI improvements. So you might have seen, so on here, you have to, as you hover over things, it's generally fast, but for larger applications, you might see a little bit of a delay. Also on the timeline view of things, what we've seen, so let me point that out here. So when you're looking at the timeline, we don't have labels on these. And so you have to hover over them to sort of see what the function names are and stuff. So we'll be making a lot of improvements in this area, as well as the first page that you get, the overview page, will be completely revamping this page. So what you notice that there's a lack of here is that you don't have access to sort of the report from equivalent to Pat report in a graphical form. You can click this text box and you can get the actual text report from the application, but there's not a graphical way to sort of manipulate that report. So we'll be adding a way to do that. So we'll be replacing this overview with essentially like a flame graph view of your application. So something similar to what this looks like up here on the host side, except a much improved visual aspect to it for better user experience. And then in addition to that, we'll be adding basically a report view to where you can collapse and expand all of the hierarchy for the report, and then provide custom filtering options. So similar to how I told you about how you can edit those -big O files, we'll be including a mechanism for you to basically create your custom report in an easy way. So where all those different options will naturally be available to you in that view, and you can simply just click around to customize your report rather than editing one of those text files. So that's to come. There's no exact ETA on that. We'll anticipating to be working on that through the rest of the year. So hopefully maybe by the December release, we'll have some improvements around that area. Okay, so yeah, does anyone have any questions?
Wonderful. First of all, thanks a lot, James, for taking your time and showing us all of this. Maybe I can start with a question while the others think. You said that, it works, all these tools work with the Cray compiler, but I think you mentioned they also work with other compilers. So what's the trick to get those running with like the GNU compiler or any other compiler?
There is no trick. So you just have your compiler that you wish and have that loaded, and everything that I've shown you is exactly the same. So
just loading the compiler I want to use and loading the tools I want to use, and that's it.
So to be clear, so you have to use the programming environment module, right, for that compiler. So if you're you can, if you use prog env Cray, that's the Cray compiler, or you could use the GNU compiler, Intel compiler, etc. Like any compiler, as long as there's a PRG env for that, and you're using the compiler wrappers CC, big CC, and FTN, then everything is seamless, right?
Okay, it's definitely something we'll try. Okay, I think Tony is the first one with another question.
Yeah, it's sort of a follow-up. I'll lower my hand now. It's sort of a follow-up on what you've just been talking about. So Ookami is a commodity system. It's not one of the Shasta XC or whatever systems. So we don't have Alps and the Cray MPitch and all those other lovely things. So how much of this applies to that kind of environment?
Yeah, so I guess the workload manager, or the specific MPI that you're using, as long as you're using an MPitch based MPI, there shouldn't be any problems there. Like I said, the only thing that you have to worry about is the compilation aspect. So as long as you're using the CC wrappers, then stuff should just work. If you're not, then I can give you some tips on how to put some commands within your build system that will automatically insert stuff for you.
Okay. So, I mean, on our system, the Cray MPI module is MVA pitch based. And we also have OpenMPI, which is my sort of thing.
Oh, I see. Okay, yeah. So we don't support OpenMPI with Perftools. So you can still use Perftools. You cannot use the MPI based wrappers.
All right, that goes on my wish list then.
Sorry.
I'm sure that's what Barbara is there for, right?
The MVAPitch stuff will work, but not OpenMPI.
Okay.
Anybody else with questions?
Hopefully an easier one than I opened with.
Killing me here.
Right, Gerard.
All right, so my question would actually be, is it available to all systems, or does it have to be a Cray system?
You have to use it on a system that is licensed to use the Cray programming environment.
Okay, I see.
Yeah, so you cannot transfer it to a laptop and use it there or something. So
okay, so practically that would be an HP cluster these days.
Yes. Yeah. So yeah, as long as so I'm not a licensing expert, right? So, I develop these tools. I don't handle all the legal stuff, but it's my understanding that, as long as you're running it on a system that has, when you purchase a system and it has the PE license, then you're fine to run it there.
Okay, thank you.
James, do you or maybe somebody else still have the browser open with the link to the documentation? Could paste that into the chat, because I was too slow getting that.
Yeah,
Perfect, thank you.
I'll paste it with the search string and hopefully that comes up. Yeah.
Thanks.
Yeah, and then the latest one. I'll just click on that one.
Okay. Perfect. Got that. Yeah, I have the feeling that these tools are really, really useful, but not beginner tools. So you nearly need to know what you're doing to go through the documentation and everything to properly use it.
Yes, and that's
so
why
it will take some practice.
Yeah, and that's why I heavily emphasized on my demo here with me searching through the documentation to show you how to find that stuff, right? Because yes, while it's very easy to get started. Like I said, you just load the light modules, and you can you can immediately get a report after your application executes. But it's how you need to start understanding where the bottlenecks are, right? And how do you identify where in your code that you need to actually make improvements to is the hard part, right? So we provide all the data, we give you the ability to dig deeper into those, but it's up to you right now to have that idea of how to do that performance optimization. So I will give you a little bit of a heads up. I can't tell you exactly when it'll come out, or what it'll fully entail, but we are working on both a couple new documents that will contain full examples of going through an application that is not, so to say, well written, and using Perftools on it and going through and doing performance optimizations on that application. So giving you exactly that full range, right, of where you can identify stuff, and then how do you actually fix it using the HPE Cray tools, right? So we are working on that. Can't promise when it'll come out, but that is something that we're working on to help improve the user experience, to get people up to speed, and for people who aren't necessarily performance optimization experts, and to provide them with some techniques to work with their code.
That would be wonderful.
Yes, I agree. That would be super helpful.
That's
the kind of tutorial. Yeah. Looking forward to that.
Yeah.
Okay. Any other questions? I don't see a hand, I think. No. Oh, I'm pretty sure we will have more questions when we play around with it on our own, and like run into the problems or don't know how to proceed. Can we contact you then? Because you kindly put your email there. Is it okay if we can? Okay.
Yeah. So feel free. If you have any follow-up questions, you have my email. I'm always open to answering questions. I'm especially interested in feedback in how with your experience with our tools, right, or the programming environment in general. Don't just tell me the good things. Please tell me the good things, but also tell me the bad things, right? Because if there's something that you find hard to use, I want to improve that. And that's something that has been big on my list this year, is to make a lot of improvements. And like I said, one of those things is sort of revamping the Apprentice 2 GUI, and trying to provide new documentation for users to help get them up to speed faster, things like that. So, I'm open to all feedback.
Wonderful. I think you definitely will get some from our side and from our users too.
Yeah. How about trying to set up a tunathon or something?
Yeah.
If that's a word.
Yeah, we've had we've had some experience with that in the past. So with some of our with some of our other customers, we participated in some of the hackathons that they've had. So yeah, we rely, it's not something that we have really hosted ourselves, but we rely on the users to actually, try stuff out, and we're there to act as like a resource to help you understand how to use the tools and things like that. So
yeah.
Yes, I would have to follow up to talk to some other people to get permission to do that. But yeah, if you're interested in that, I can definitely, send that along, and we might be able to set something up.
Okay, great. Then thanks again, James, for your time and for showing us all this. And
thank you.
Everybody, the recording will be on the website as usual in the documentation or in the support section. I will post a link in the Slack when it's there, and you can have a look again and go through the material again. Okay, thanks everyone for joining, and have a nice rest of the day.
Thank you very much. Hope you enjoyed it.